Hey everyone, Mr. Schachter here to compare definite integrals to antiderivatives. Before we get started, let's do a brief refresher on what an antiderivative is. So suppose I have a function f of x to be 2. Antiderivative, capital F of x, we always use capital letters for antiderivatives. Capital F of x could be 2x because the derivative of 2x is equal to 2. Another possibility is actually 2x plus 1. Or a third possibility is 2x plus 2. These three functions, if I took the derivative of them, would equal my original function f of x, right? So we can actually just summarize my antiderivative family to be 2x plus c. And I know now that this is the family of functions that if you take the derivative of them, you would get the original function f of x equals 2. Well, we also know enough about integrals now to understand that if I took the derivative of an integral, I would actually end up back at f of x, right? Think about it. Integration sends us backwards, so we know if we were at velocity, we'd go back to position. So if I took the derivative of the integral, they would essentially just undo one another, and we'd end up back where we started. But if that's true, that means that antiderivatives and integrals are really doing the same thing, because I know my integral, or my antiderivative rather, will also send me back to the original function f of x. So it turns out that antiderivatives and integrals differ by a constant. That plus c constant is the difference between an integral and an antiderivative. Also, as I summarized on the first slide, the derivative of an integral is equal to the original function f of x itself. And we can use this fact to prove something even more useful. If I start by looking at the integral without taking its derivative, the integral from a to x of f of t dt is just going to equal the antiderivative capital F of x plus c, as we summarized on the previous slide. And if I can pick any value for x that I want, just to prove my point for a moment, the integral from a to a of f of t dt is equal to f of a plus c if I let x be a. And this is really helpful because I know the integral from a to a of f of t of anything is 0. So 0 is equal to f of a plus c. And if I minus c on both sides, I get that c is equal to negative f of a if I minus the f of a or multiply by negative 1. And this is really useful because now I can actually summarize what my integral actually is. That the integral from a to x of f of t dt is actually just equal to the antiderivative evaluated at x minus the antiderivative evaluated at a. And this piece of information right here is actually part of the fundamental theorem of calculus. So the fundamental theorem of calculus has two parts. The first part is the statement on the previous slide that is very, very complex, and we'll actually spend a long time dissecting it. But for now, we're going to just focus on the second part of the fundamental theorem of calculus, which states that if f is continuous on a closed interval, and if capital F is an antiderivative of f on a to b, and then the integral from a to b of f of x dx is equal to the antiderivative at b minus the antiderivative at a. And we call this the integral evaluation theorem. This is the theorem we're going to use to solve integrals. All of our integrals that we're going to need to solve, this is our theorem. Real quick, before we try a problem, I just wanted to give you the official polynomial integration shortcut. So if you're taking the antiderivative of any function, the shortcut is you take your original polynomial and you raise it to the n plus 1 power. That means you basically increase the power by 1. And then you divide by that same increased power. If it's an indefinite integral, meaning an unbounded integral, you have to add the plus c, but that's only in chapter 6. I copied and pasted this from chapter 6, so you don't need to worry about the plus c for now. I just wanted you all to make sure you had this. Let me just show you a quick example of what it looks like. So suppose you had the function 3x squared, and I asked you, find the antiderivative. If that's the original function f of x, which we'll just call f of x, the antiderivative of f of x is equal to, let's apply the new theorem. So the function stays 3x, but the power increases by 1. So if you increase 2 by 1, you get 3. and then you divide by that same 2 plus 1, which was 3. And if you simplify this, the 3's cancel and you get x cubed. So we all know that. If you took the derivative of x cubed, you got 3x squared. But now you know the official polynomial shortcut to integrate. Let's try an example. So the example is the integral from 0 to 5 of x squared plus 3x dx. Step 1 is to find the antiderivative of this function f of x. So the antiderivative of x squared would be x to the third over 3. A quick check, if you took the derivative of x to the third over 3, you would get x squared because the 3 and the 3 cancel. Reduce the power by 1, you get 2. That's that. And the antiderivative of 3x is 3x squared over 2. Again, if you did a quick check and took the derivative of 3x squared over 2, you would in fact get 3x. But this is an integral, not just an antiderivative. So when you are integrating something that has bounds, you put your expression in brackets. And the bounds of the integral shift to the end after you've taken the antiderivative. Okay? We're then going to plug in the top value first, and then the bottom value second, and we're going to subtract them. Essentially what we're doing is we're using the fundamental theorem of calculus, which says to take the antiderivative evaluated at 5 and subtract the antiderivative evaluated at 0. The antiderivative, of course, is the function x cubed over 3 plus 3x squared over 2. So in order to calculate the integral, we simply have to plug the 5 into the function, the antiderivative. So that would be 5 cubed over 3 plus 3 times 5 squared over 2. That's part 1. That is this, f of 5. That's what this is right here. Then we're going to do a minus, and we're going to do it again, but we're going to plug in 0. So this is 0 cubed over 3 plus 3 times 0 squared over 2. And I'll try to use a different color highlighter. I'm not sure it'll show up nicely, but f of 0 is this piece right here. So this is the fundamental theorem of calculus part 2 that helps us evaluate the integrals. Well, nice that the 0 and the 0 actually just end up making 0, so this whole thing goes bye-bye. So the answer is just 5 cubed, which is 125 over 3, plus 5 squared is 25 times 3 is 75 over 2. And if you add these things together, you can get a common denominator, and I think it comes out to 79.16 approximately. That is what the integral is actually equal to. And we use calculus now to solve them.